Avdi, today I'm going to discuss how to use Python scikit-learn to do the clustering. As we discussed in the class, there are many clustering algorithms out there, and depending on which one you are using, you may get different results. And this is from scikit-learn website. Basically, they show how different clustering algorithms are resulting, as I mentioned, different resulting different cluster, right? We are going to do K-means algorithm, spectral clustering, and agglomerative clustering, right? But because we are using scikit-learn, honestly, we could just switch between any of them quickly with a line of code, but I will just show you 3 of them. Right, we are going to use the cancer research dataset, and I'll remind you more about the data file in a bit. We are importing pandas, numpy, and matplotlib for operations. Let me run the first line and read the data. So we have the patient ID and some measurements. At the end, we have benign or malignant classifications. First, as I have done in the past, I'm going to set the patient ID as the ID. And then for benign malignant classification, I'm going to just introduce 0, 1. Honestly, this is a clustering algorithm, so I don't I should not have this category, but I'm going to just have it to show you how the clustering algorithm works by comparing with the results we already know, right? And then basically introduce a dummy variable. It is binary, so I need two variables, benign and malignant. That means one binary, 0, 1. There is a non-value. I'm going to drop all of them and then we'll check the data set. Right, so I cleaned all the NAs basically. At this point, I can start defining my X and Y variables. Again, when I'm doing the cluster analysis, I shouldn't know the Y variables. I'm working with the data set with the Y variables just to show you, right? And make it easy to explain. So I have Y variables, and that is cancer file, right? Drop the class malignant. That is basically after I convert this, it becomes, actually, let me show you that one first. Cancer, right? So I'm gonna drop this one for the X variable. Copy paste, okay. Class malignant. I should correct this data, but there is an empty space over there, and we are gonna drop the entire axis or column, right? And then my Y variable is cancer malignant, basically. And then all right, and there are double S C's over there. Okay, so if you guys remember, so we are gonna do some mathematical operations. It could be squaring or multiplying the numbers. That means the scale of these numbers are important. These are 9 to 10, I see, then 10. At most, it looks like 10, but then there are zeros and ones as well. So I should always consider scaling the parameters. So I'm going to use that scaling from scikit-learn by pre-processing it, right? And import, I'm going to just use min-max scaler, right? And then I will run my scaler on my min-max scaler, and then go through the scaler and fit my X variables to this scaler, right? That is how we do it. Fit dot, if I can press the dot key, right? And I'm gonna put the X variables in it. Right. Once I'm done with that, I'm gonna define my new x variables as the scaled version of basically x variables, right? Right. So there were some integers and so forth. They were converted to ratios, right? Float basically, and that's fine. Now, one thing I want to do is, like, when I create all these things, I would like to create a figure of two clusters, and for that I'm gonna need a manageable dimension. At this point, I have about 10 or 11 attributes, and if I try to do basically represent this, I need a 10-dimensional space, which we cannot comprehend or understand. So one way at this point is to use the principal component analysis and reduce the dimension of it, or use one of the built-in scikit function to do the same thing again. So I'm going to use the scikit TSA, and that is T distribution. Basically, it reduces the dimension using some kind of T distribution probability. And let me do that. And for that, again, I need to introduce from scikit-learn manifold. All right, import tsne, right? And then I'm gonna say, actually, let me run this one. tsne, I'm going to say that is equal to tsne open parentheses. Let's check the the function, right? So I can, at this point, again, if I want, T distributed stochastic neighborhood embedding, and idea is to again visualize the high dimensional data in its two-dimensional space. And I can define, of course, all these parameters, and then with that it gives me an estimate of data into two-dimensional space. I'm gonna define the let me see, perplexity, and then definition says basically is related to the number of nearest neighborhood that is used the other manifold learning algorithms. So for larger data set, you'll use larger numbers. I'm gonna just say it is 40, but I haven't really experimented with it, right? So let me add that one. Right, and then I could define the number of iteration, basically, like it is reducing, but how many, right? Times it's gonna go over these calculations to get me to two-dimensional space. Let me put a large number here, right? And then once that is done, of course, as always, we are gonna fit the data. This time I'm gonna say basically from this clump thickness to mitosis, I'm gonna reduce all of them to a two-dimensional attribute, and I'm gonna call that one my new x, basically. All right, and that is tsne, right? I'm gonna fit. All right, while fitting, I'm gonna transpose actually. Okay, basically I'm transposing or transforming, actually transforming the x values that I had, right? Again, all this is to just visualize the data, right? So it's working, and hopefully I will get some results shortly. It should take about 10 seconds or so. Right? So then, all right, I should also actually do the clustering algorithm. So from scikit-learn cluster, let's import the Kmeans, right? And as you know, whenever we do this, we are gonna say K-means. I'm defining a K-means model basically, and for that I'm going to say that is K-means. Similar to all other scikit-learn function we learned, for the K-means I can define a lot of things. Let me run this so it knows I'm doing the K-means algorithm, right? So I can define the number of cluster, how I'm gonna initialize it, and so forth, right? At this point, I'm gonna stop for a second and go over a representation of what K-means actually does, right? Now, this is a data set or data visualization tool. It's going to show us how the K-means algorithm works. At this point, basically, it randomly chose that these red, purple, green, and bluish, I'd say cyan ring colors are the center of clusters, right? And then with that, it's going to say who are the closest points to these centers, right? And in the next step, it will move or calculate the center of a cluster based on the data that it thought it is closest to, right? Once that is done, it's gonna go and rearrange because it's moved the center from here to there, and at that point the closest point might have changed. That's what happened, right? It's gonna do this one again, move the center, now recalculate what is the closest point to each center, assign some of them, reassign, and then move the cluster centers and reassign the nodes. There was just one, and then move the cluster centers a little bit, see if there is any more actions, and keep doing this until there is no basically change in the data set. Hopefully at one point we are gonna stop, right? At this point, basically we found the 4 cluster, and that was something I said already. So this is the cluster. Remember, we've started 1 cluster here and 3 of them around this area, but by just doing that iterative process, it kind of converged to a solution, right? And depending on where we start, the end result might be slightly different, right? I keep that one in mind, right? So that is what we are gonna do basically with our data. We are gonna calculate the distance, and this is in a 2-dimensional space again, like plane, but our data has like 10 dimensional, so these calculations are more convoluted, but at the end it's a simple square Euclidean type of a calculation, right? So let me go back to our code. Right, so K-means I could, so we know what we are doing now. So I'm gonna just say, I can define all of these, but I'm gonna just define the number of clusters, right? And because we know we have like benign and malignant type of cancer cells, I'm gonna even go cheat in this case and say that those are 2 I have, right? As we have always done, once we know the, I guess once we create the model, we are gonna fit the model, and that is KMNS fit, right? Now, because this is a clustering algorithm, we are gonna only fit the X, right? In the past, when we used the regression or classification algorithm, we always said, okay, X training and Y training. And if you realize, I didn't even create X training and Y training at this point, right? So I'm gonna just need the X variable basically, right? And I could also set the others, but I'm gonna just say X variables, and that is my X vars that I defined earlier, basically everything but the class malignant category, right? And then actually I don't need this, right? So I fit. Now I'm gonna assign the prediction, or I create a prediction, and I will assign those predictions to my K-means Y kind of array, and then I will say that is X. Right? So what I've done, I know this is the two-dimensional thing. You remember I created a two-dimensional basically cluster or two-dimensional data. I'm gonna use that two-dimensional data to create a cluster. Now I could skip those and then basically do a higher dimension, but that's okay. But I'm just gonna see how does it look, but I could just play with the original data X bars and then do the rest of the calculation. I just created two clusters. The next step is basically fitting my data. Now when I'm fitting the data, I could go fit the original X vars, right? That 10 attribute data, and then do all those calculation and see how those two cluster look like, but then I cannot visualize. So I'm gonna ignore the X variables, right? Just for the sake of visualization, right? And then focus on the X, right? So when I'm fitting my function, I'm gonna actually say fit the capital X rather than X variables, right? But we could do the other one as well, right? So let me say KMNS fit, and if you look at the fit function this time, it only takes the X because this is a clustering algorithm. It does not know the Y, and I didn't even define X var and Y, X training, Y training kind of an process. I'm just gonna go do everything, but I could also do those, right? I could just create X bar and Y bar, create a clustering algorithm, and then check to see if that clustering algorithm is performing well on my data, right? The data that I know the clusters already, right? And right, so I'm gonna do this, and then I'm going to say the Y variable for the K-means is going to be as predict, right? And again X, right? So now what I have a prediction. I have X variables that I transform from 10 or so dimension to 2 dimension for visualization, and for that X I created a K-means basically cluster, and then I also know what is the original cluster, which is Y, basically Y var that I defined earlier, right? So right here. So I have all those information, so I can just start plotting this thing and see how this function look like, right? All right, next I'm going to start drawing or visualizing the plot. So I'm going to say there are two basically figures, AX1 and AX2, and they are going to be equal to PLT that subplots right. So now if I look into it, I can define a couple of things. Number of rows, number of columns of figures. So let's say I'm creating two figures. Do I want them to be on a single row, like side by side, or up and down? So basically that defines this. So I'm gonna draw two. I'm gonna say there is one row, two, and then they are gonna share one of the axes, right? And I'll define that axis later, right? And then the first figure, it's going to be a scatter graph, right? So my scatter graph will have the x of, basically when I did this transformation here, it is no longer a data frame, but it is an array, so I need to treat as such. So for array, I'm saying that the column 0 all the elements in the X array column 0, and then the column 1 right. Then C, the Y is basically KY, that would be my first. CMap is basically if I'm using basically color map, and in this case the Y is an array too, that's why I'm using the CMap, right? CMap, and then that is equal to red, edge color equal to none, and then alpha is basically the transparency, if two dots are behind each other, how transparent I want the one at the top to be, right? And then I'm gonna call this one as set title, Kmeans cluster, right? And I'm gonna create same way the second figure that is based on this is based on the prediction. Remember, chi-y was a prediction, right, from the K-means. And this time it is the figure 2, right? But instead of calling ky, I'm gonna call my y variables as they are here, right? And everything else could be the same. I'm gonna say this is actual cluster, right? So these are the don't mind the coloring. Basically, this is my actual cluster, right? And most of them seems to be clustered correctly. This area here, the K-means clustering says it is actually mostly one way or another, and then whereas in reality they are mix of it. So what would happen if I have 3 clusters here? Just let's run for sake of it. So of course my actual cluster doesn't change because I have 2 classification, benign and malignant, but then it divides it to the 3. If I have 4 clusters, if I force the model to have 4 clusters, right, so it divides this way. So I could just basically change the cluster numbers and hopefully look into the real data and say what number of cluster makes the perfect sense for my situation, right? Now next, let me correct this or change it to 2 clusters, right? Now it is the same color. As I said, it just randomly picks them, right? Let's do the spectral clustering, right? Right, so the same idea. This time I'm calling the spectral clustering, number of clustering, and all those other parameters needed. I added them, and then just call the figure, right? This is the spectral clustering. It looks like a little bit better compared to the original K-means, but I really don't know at this point without a measurement. And remember, in reality, we wouldn't even know what is the actual cluster, right? So, and then I can do the hierarchical clustering, right? Same idea. So it divides in the middle somehow, and then I have that cluster, right? So different clustering algorithms basically ends up with different results. And again, remember, I did reduce the number of attributes or the dimensions from 10 or so to 2 to just to basically visualize it. I didn't need to go through this step. And if I didn't do that, I would have basically still create two clusters, but then I wouldn't be able to create a visual of it, right? So this step here, basically these two lines, helps me to visualize the data, right, in a meaningful way, right? So that's it.